Okay. So today going to wrap up chapter 5 on eigenvalues and eigenvectors, and then next week we have just 2 sections to cover from chapter 6, and that'll be everything. So here we're going to look at diagonalization, where we obtain the eigenvalues and eigenvectors of a matrix A like before, but then we use that to try to factorize of a matrix. So what it means for a matrix to be diagonalizable is if it is possible to factor A to a product of some invertible matrix P, so it has to be invertible, times a diagonal matrix D. So a diagonal matrix is a matrix where all the entries are 0 except the entries along the main diagonal, and then times P inverse, which is why P has to be invertible. So if it is possible to obtain its factorization, we say it's diagonalizable. Now, how do we get these matrices P and D in this diagonalization? It's related to the eigenvalues and eigenvectors. So if this factorization exists, then the numbers along the main diagonal of D, those are the eigenvalues. So this is how we obtain this factorization. We compute the eigenvalues and eigenvectors. The eigenvectors corresponding to these eigenvalues are the columns of the matrix P. But P has to be invertible. So the only way this works is if we can actually find, if A is n by n, we need to find n eigenvectors that are linearly independent, because they have to be linearly independent in order for the matrix P to have an inverse. So what that means is a given n by n matrix A is not necessarily diagonalizable, because there are matrices that do not have enough linearly independent eigenvectors. Now, how can you tell if a matrix is diagonalizable or not? It's not always easy. So one simple case is if you get all the eigenvalues of A, like by getting a roots of this characteristic polynomial, for instance, then every eigenvalue is going to have at least one eigenvector that goes with it. So if you have n distinct eigenvalues, then each one of those eigenvalues is going to have at least one linearly independent eigenvector that goes with it. So in that case, you have enough, and so it's diagonalizable in that case. So if you have n by n matrix A, n distinct eigenvalues, yes, it is diagonalizable. So for each eigenvalue, you find the one eigenvector corresponding to it, and those eigenvectors are the columns of P. The other possibility is, what if the eigenvalues are not all distinct? What if you get the roots of your characteristic equation and you find that some eigenvalue is a repeated root? Then it's a bit murky in that case. It may or may not be diagonalizable. It just depends on the eigenvectors. So the only definitive statement I can give you is this one. If you have an eigenvalue that repeats m times as a root of a characteristic equation, so that's a multiplicity of the eigenvalue, then you had to be able to find that many linearly independent eigenvectors. So you row reduce this matrix A minus lambda I, because you would do that to get the eigenvalues anyway, because the eigenvectors are from a null space of this matrix. So if a multiplicity is m, then when you find a null space of this matrix, it has to have dimension m. So whatever multiplicity of the eigenvalue is, you have to be able to find that many free variables. If you don't have enough, then it's not diagonalizable. But if you do have enough, then yes, it is. So, and this is only going to come up if you have a repeated eigenvalue. Now, why is diagonalization important? There are many applications where it's needed to compute a function of a matrix. For example, you can think of the inverse as a function of a matrix, but also a matrix exponential or powers of a matrix. All of those come in handy for various applications. And computing a function of a matrix is not easy because that involves matrix multiplication. That's an expensive operation. But if you are able to diagonalize A, then it turns out that you can raise A to a power just by raising D to that power and then multiplying on the left by P and the right by P inverse. And taking a power of a diagonal matrix is easy because all you're doing is you're just raising the diagonal entries to that power. So because of this, having that diagonalization can save a lot of computation. The reason why this works, suppose I want to do the simplest case of A squared. So A squared, well, that'd be the same as PDP inverse, the whole thing squared. So then if I write out what this is, so PDP inverse, but then we'll look what happens in the middle here. The P inverse and the P will cancel each other out. That product is identity. So that's why you end up with P D squared P inverse. And you can see, imagine how this would carry over to any power of A. And also other functions of A, like the exponential, because you can think of matrix exponential in terms of its Taylor series, which would again involve powers of A. So what we're going to see here in the problems is for a given matrix, determining whether it is diagonalizable. If so, finding the matrices P and D, which come from getting the eigenvectors and eigenvalues, and also using the diagonalization, if it has one, to easily compute powers of a matrix using this. So first couple problems are about computing powers. So here, we're not even given the matrix A in this case, right? Because that's not what we need for this problem. We are just given this factorization. So here we're given P and D. And we could use P and D to reconstruct A, but it's really just A to the fourth that we want. So what do we do? So A to the fourth is written as PDP inverse, all raised to the fourth power. But using what I showed you a little while ago, that's the same as computing just P times D to the fourth times P inverse. So now I need to fill in all the pieces. So here's P that was given, D that was given, and then we're going to need P inverse. So to get the inverse, remember the formula for the inverse of a 2 by 2 matrix you swap the diagonal entries. That's what I've done here. And then the off-diagonal entries are negated. And from what's written here, looks like that's everything. But can anyone tell me, in computing the inverse of this matrix, what step did I leave out from a formula for a 2x2 inverse? So aside from getting the entries here from this, what else am I supposed to do to get the inverse? Supposed to divide by something. What is that?
Is it the determinant?
Yes. So the formula for the inverse of a 2x2 calls for dividing by the determinant. Can anyone tell me why I didn't actually have to explicitly do that in this case? What is the determinant?
One.
Yeah, the determinant is 1 because it's 1 times 5 minus 2 times minus 2, so 5 minus 4. So 1 is determinant, so there was no need to divide by anything here. Okay. So this right here, that's our P inverse. Now I want a to the 4th. That means we're raising d to the 4th power, so that's done here. So now all I have to do is multiply these three matrices together, P, d to the 4th, P inverse, and then I'm done. I'll have a to the 4th. Now, what I did to get from this step to this step is I multiplied this matrix P on the right by the diagonal matrix d to the 4th. Now, when you're multiplying on the right by a diagonal matrix, that means you're scaling the columns by these diagonal entries. So what that means is this first column is multiplied by 1, so it stays the same. This column, second column, is multiplied by 1/16. So that's what gives these entries here. All right. So now I just have this whole thing here is P d to the 4th. Here's P inverse. So now I just carry out the multiplication of these matrices, and that gives me the final result here. Okay, I'm gonna throw in a little additional info here. Okay. Oh wait, not there. For this step. Just to flesh out the multiplication of these matrices. 1 times 5 plus minus 1/8 times 2. And then 1 times 2 minus 1/8 times 1. And then I have minus 2 times 5 plus 5/16 times 2. And then finally minus 2 times 2 plus 5/16 times 1. So that's where all of these entries in the product came from. And I also want to indicate that when you have a case of a matrix DB diagonal, and you're doing a product like this, multiplying on the right by diagonal matrix, scaling each column of A by a corresponding diagonal entry of D. So for example, second column of A is multiplied by the second diagonal entry of D. And although it wasn't necessary in this problem, but it may come up elsewhere, if you're multiplying by diagonal matrix on the left, then you're scaling rows. All right. So that way you don't have to go through this whole process whenever you're multiplying by a diagonal matrix. You can just keep in mind that you're scaling columns or rows, depending on which product it is. All right, so questions about this problem? Now, this next one is similar, but we're computing a general power, a to the k. And here we're given a matrix A, but now we're given its full factorization. This matrix, this is matrix P right here, it has a determinant of -1. So to get the inverse, okay, you swap the diagonal entries, you negate the off-diagonal entries, but then you have to divide by -1 because that's the determinant, and that ends up negating the whole thing. And here's your matrix D right here. So we proceed in the same manner. That a to the k is just going to be p times d to the k, p inverse. So now you can exponentiate by raising the diagonal entries of d to the kth power. And all that's left is to carry out the multiplication of these three matrices. So I do the same thing as in the previous problem, where I'm multiplying this matrix P by diagonal matrix D to the K on the right. So I'm scaling the columns of P by these diagonal entries. So here we see the first column get multiplied by 3 to the K, and then the second column gets multiplied by 1. So it's just reproduced right here. And now all that's left is to multiply this matrix, which is P d to the K, by P inverse. And this is a result here. So we see how the exponent K impacts the entries of a to the K. Now we see these 3 to the K's in here because that's one of the eigenvalues. So remember, in this factorization, 3 and 1 are the eigenvalues of A, and then the eigenvector corresponding to eigenvalue 3 is this one, 3, 1, and then an eigenvector corresponding to the eigenvalue 1 is this sector, 4 and 1. Do the same thing here that I did in the previous one. All right, so that's the 1, 1 entry from the first row and first column. And then for the doing the first row and second column to get the row 1 column 2 entry. Then for the second row, first column and then second column. Okay. So you can see where the entries of a product came from. Any questions on this one? I missed. Okay. So here we have a matrix that may or may not be diagonalizable. So the idea is to try to find a diagonalization. Although in this case, we can actually tell by looking, just by inspection, that this matrix is diagonalizable. How can we tell that quickly that it is? It has to do with the eigenvalues that we see here. Okay. Look back here. What's a quick way to tell if a matrix is diagonalizable? That's the answer is on this page. Come on. The eigenvalues of a matrix given are plus and minus 7. The eigenvalues are all distinct. That's the point made here. If all the eigenvalues are distinct, it definitely is diagonalizable. We're able to see what the eigenvalues are plus or minus 7 because the matrix is triangular, so you just read them off the diagonal. So that's I can tell right away from them being distinct. That's diagonalizable. If it's just been 7 and 7, then actually in that case it would not have been. So for each of these eigenvalues, it's necessary to find an eigenvector that goes with them. So what we do, starting with the first eigenvalue of 7, we take our original matrix minus 7 times the identity. So it's A minus lambda identity. And times the eigenvector must be equal to 0. So this matrix worked out is right here. That times the eigenvector 0. So now so this matrix is one we want to work with, but it's already essentially row reduced. There's nothing more to gain by any row operations. We can see that this entry is the only pivot position we have. And therefore, the second unknown, which I'm calling P21, that is a free variable. And that's what we need. There has to be a free variable for this system to have a non-trivial solution. That would be an eigenvector. Now, how I'm labeling these entries, I'm looking for the eigenvector P1. So 1 is the second index. The first index is their components. So P11, first component, P21, second component of eigenvector number 1. So that's how I'm going to number these things throughout. So the second unknown, P21 is a free variable. So we go ahead and set it to 1. So then we use this equation to solve for the other unknown, P11. So minus 14 gets moved to the other, multiplied by P21, it's moved to the other side. So P11 will be 14. Remember, it's moved to the other side, so the sign changes. 14 times P21 divided by 8, and we get 7/4. So this is a solution, a non-trivial solution of this system of equations, 7/4 and 1. But we'd like to have nice numbers if we can. So if I go ahead and multiply this entire vector by 4, then I get the eigenvector 7/4. So this would be the first column of P. Now I do the same thing to get eigenvector P2 corresponding to the other eigenvalue, minus 7. So I have matrix minus 7 times the identity. So you work all this out, and this is the matrix that you get now. So using row operations, which I'm not going to bother to carry out here, but this column's entirely 0, so there's no pivot position here. This is the only pivot position. So P22 is a free variable, which is what we'd expect for a system like this. So then if you write out what the equation is, 14 times P12 plus 0 equals 0. So that means that P12 has to be 0. And then the free variable you can set to anything you want, as long as it's non-zero. That's very important. Anytime you're trying to get a non-zero solution, so any free variable you have should set to something. if you only have one free variable, it needs to be set to something
It's
non-zero.
for, not from.
I'm sorry, what?
Form, not from.
Okay. Wait. I'm sorry, are you pointing out a typo?
Sorry.
Okay. Actually, if there was a typo, I need to say this equal to 1, not 0. Okay. All right. So we set a free variable equal to 1. It's got to be set to something non-zero. From this equation, we see the other unknown p12 is 0. So this is our eigenvector for the second eigenvalue, -7. So here we have our two eigenvectors, p1, p2. They are not multiples of each other, so they are linearly independent. So that means the matrix is diagonalizable. So if we put the two eigenvectors as columns of P, that's our matrix P, and then the eigenvectors fill the diagonal of the matrix D. So original matrix A can be written as P, D, P inverse, but for entering your answer in MyLabs, only P and D are required. You don't have to compute P inverse. Now, make sure when you form your matrix P and D that the eigenvectors and eigenvalues correspond. So for the first eigenvalue was equal to +7, so its eigenvector fills the first column. And then the second eigenvalue is -7, so its eigenvector fills the second column. Now, the order itself doesn't matter as long as the ordering is consistent. So for example, I could swap these eigenvalues as long as I swap the columns too. It's PDP inverse would still lead to the same matrix A in this case. Okay. All right, so this is how we find out if a matrix is diagonalizable. For each eigenvalue, find any linearly independent eigenvectors that go with them. If it's an n by n matrix and we have a total of n eigenvectors, then it is diagonalizable. Eigenvectors are the columns of P, eigenvalues are the diagonal entries of D. For this next one, this matrix is not triangular, so we can't simply read the eigenvalues off a matrix. So we have a little work to do to get the eigenvalues. We need to do the same thing as in a previous section from Monday, get the characteristic polynomial. So here, this is a determinant of the matrix minus lambda identity. So you subtract lambda from only the diagonal entries. So then you take the determinant and you get, after foiling everything out, here's a characteristic polynomial. And it factors nicely into lambda -5 whole thing squared. So from this, we set this equal to 0 and we see what the eigenvalues are. We have only one eigenvalue, one distinct eigenvalue of 5. And because it's lambda -5 squared, then it has multiplicity too. So it's a repeated eigenvalue. So now we want to find eigenvectors. So we look at the original matrix -5 times identity. And this is what we get. So then from row operations, you can just add these two rows together and the second row is all zeros. So this matrix is row equivalent to this one. So you can get this matrix by performing row operations on this one. But what we have here is this element is our pivot position. this is our free variable. So we could use that to get an eigenvector, but here's a problem. The eigenvalue 5 has multiplicity 2. We only have one free variable. That's not enough. So that means that we're only going to be able to find, if a null space is dimension 1, so we're only going to be able to find one linearly independent eigenvector. So we've fallen short. We need 2 linearly independent eigenvectors to get a diagonalizable matrix. So our conclusion is the matrix is not diagonalizable because you can't get enough eigenvectors. So you're comparing the multiplicity of the eigenvalue, 2 in this case, to the number of free variables that you get from this matrix. If this has less, for any eigenvalue, if it's less, not diagonalizable. All right, here for this matrix, thankfully we're given the eigenvalues. You see they're all distinct. So that tells us right away this matrix is diagonalizable. Well, we're told to diagonalize it, but here's how you can tell that it can be done. So what we need to do is for each one of these eigenvalues, 1, 4, and 5, we need to find an eigenvector, and those would be the columns of the matrix P in our diagonalization. So what we go through, this is kind of a lengthy problem. You go through this process 3 times. I have a matrix minus 1 times identity, and we get this. So now the idea is to perform row operations on this matrix, reduce it to echelon form, and we should get a free variable. If not, something has gone wrong. And then we can use that free variable to get an eigenvector. So first I go ahead and perform row operations to eliminate in the first column. And then I move on to the second column and eliminate this entry of a minus 10. Thankfully, the numbers work out pretty nicely. I do some scaling to make the numbers a little smaller, just for convenience. So now the matrix is in echelon form. And sure enough, the third unknown, so for third column, that's a free variable. And I'm calling it P31. It's the third element of the first eigenvector. So that's my indexing convention. So this one free variable, we set it equal to 1. And then I go to this equation to get the second component, it's P21. So this equation says P21 minus P31 is equal to 0. So P21 and P31 must be the same. So I go ahead and get 1 for that. And then I go up to this equation. So I have, so P11 is equal to 7 times the second unknown minus 4 times the third unknown, because these terms are moved to the other side. And then I have to divide by this entry, 3. So I work that out, and I get 1 again. So all the components of the eigenvector are equal to 1. So that is my first eigenvector corresponding to this eigenvalue, 1. Now I have to repeat this process to get P2 and P3. So, oops, typo. I'm now moved on to the second eigenvalue, lambda 2. And I want the eigenvector P2. So I take a matrix minus 4 times the identity. So it's always eigenvalue times identity. And this is what I get. So now I'm going to perform row operations on this to solve a homogeneous system involving this matrix. So these involve elements of a first column being the same. I can just subtract row 1 from row 2 and row 3 to eliminate these entries. And then I can see that these second and third rows are parallel to each other, so I can use the second row to wipe out the third row, and then I'll just scale to make the numbers a little nicer. So now we're in echelon form, and so now I have a free variable, third unknown, so it's p free 2. So I just set it equal to 1 because I need a non-zero solution. And just like before, p22 minus p32 is 0, so these unknowns are equal. And then to get the first unknown, I have minus 14 second unknown plus 8 times the third unknown, and that gets divided by the minus 9 here. So that's all worked out, and we get 2/3. So here's our eigenvector 1, 1, and 2/3. But any multiple of an eigenvector is an eigenvector. So to make things nicer, we can just scale this by 3, and now we have this eigenvector with whole numbers. And it's not absolutely necessary, but also why not? Because it's convention to set any free variable to 1, just to guarantee you get a non-zero solution. Then you don't, who knows how you don't know how the numbers are going to work out, if they're going to be nice, until you get through everything. And then we go over this one more time. To get the third eigenvalue, it goes to the third eigenvector, it goes to the third eigenvalue, 5. So we have matrix minus 5 times the identity, and we get this. I've deviated a little bit from the usual elimination procedure just because these second and third row have the same, they're actually very identical. So I just go ahead and use the second row to wipe out the third row. So we have a row of zeros. And then to complete the elimination, I don't feel like working like I don't feel like working with fractions. So what I do is I scale the first and second rows just so these elements are the same. And then I could just go ahead and subtract the first row from the second. And get this. It's only because I didn't feel like working with fractions. So then I can scale the rows to make the numbers at least as nice as possible. Like, finding a greatest common factor of each entry in a row and dividing by it. So this is the nicest matrix I can come up with for echelon form. And once again, the third unknown is a free variable. So I set it to 1. And then I solve for the second and first unknowns like before. So here I have 4 times the second unknown is equal to 3 times the third unknown. So then I get 3/4 for the second unknown. And then I substitute second and third unknowns in this equation. So I have P13 is equal to 14 times the second unknown minus 8 times the third unknown, all divided by 10. And we get 1/4. So now my eigenvector is 1/4, 3/4, and 1. But just like before, I can scale that, and again, get something with nice numbers here. So now I can form my matrix P. It's just eigenvectors as the columns. And then form a matrix D by putting the eigenvalues along the diagonal. So the original matrix is equal to P times D times P inverse. Any questions about that very tedious process? Okay, here we have same kind of problem, except here we're only given two distinct eigenvalues. So the question is, can we find three linearly independent eigenvectors to go with them? So follow the same procedure in the last problem, matrix minus eigenvalue times the identity. And we get a matrix of all ones. So then row reduction is quite simple. You can use the first row to totally wipe out the second and third rows. And what that gives us is two free variables. So that tells us right away that the matrix will be diagonalizable because there's two free variables, the eigenvalue of 1 will have two linearly independent eigenvectors, P1 and P2. And then the eigenvalue of 4 will get us a third eigenvector because it's going to have at least one. So that'll give us three linearly independent eigenvectors altogether. So then we'll have an invertible P. But now we have to get them. So I'm going to go for this process twice with the same matrix to get vectors in the null space. I just had to set my free variables differently. So since I have two free variables, to get my first eigenvector, I'll set P12 equal to 1, the second unknown. I'll set the third unknown equal to 0. And then all my unknowns satisfy this equation. P11 plus P21 plus P31 must be equal to 0. So since all the unknowns have to sum to 0, I get P11 equal to -1. So this is my first eigenvector. For P12, I make the opposite. For P2, I make the opposite choice for my free variables. Oh, typo. Okay, I set P22 equals 0, P32 equal to 1. We have to have something non-zero in here. We can't set both of them to 0. But so here I use the free variables 1, 0 in this case, 0, 1 in this case. At least this guarantees that they're linearly independent. Then I'm solving the same equation. So I get P12 equal to -1. So that gives me this eigenvector. And these eigenvectors, you can see they're not multiples of each other. They're not parallel. So they are linearly independent. And both of these correspond to the eigenvalue that's equal to 1. That's multiplicity 2. So I have two eigenvectors. Now I just need one more. So for that, I move on to the third and final eigenvalue of 4. So I have matrix minus 4 times identity. Gives me this. So now I need to perform row operations on this matrix, see what I have as far as free variables and so forth. For convenience, I swap a first and second row so I can get a 1 up here. So then I can eliminate entries in the first column.
Can you go back? Stop. Okay.
Okay. Now, after I've used the first row to eliminate entries in the first column, you see the second and third rows are negatives of one another. So then I can just add those two rows together to wipe out the third row. And then I'll just do a little scaling to make the numbers a little nicer. So now I've reduced this to echelon form, and the third unknown is a free variable, as it should be. So I set it equal to 1. This equation gives me, so second unknown minus third unknown is 0, so they're equal. And then I substitute my second and third unknowns into this equation. So my first unknown is equal to 2 times the second unknown minus the third unknown divided by 1. So they're all equal to 1. That worked out nicely. So that is my eigenvector, or this eigenvalue. So now I can take all the eigenvectors that I found during this problem and form a matrix P with those eigenvectors as columns. And then the eigenvalues that correspond to these eigenvectors will fill the diagonal of D. And my diagonalization is complete. So the original matrix is equal to P times D times P inverse. So that problem was a little different because we had only 2 distinct eigenvalues, but one of them led to 2 free variables, so there were enough eigenvectors to go with it. But that doesn't always happen. All right. Now we try the same thing with this matrix. This is a lower triangular. So the eigenvalues, you just read them off a diagonal, 7, 7, and 9. So 7 is listed twice, so it has a multiplicity of 2. So to try to get eigenvectors, we have matrix minus 7 times the identity. And this is what we get. Almost everything is 0. Now, if we were to get this matrix into echelon form, like if we move this row of zeros to the bottom, this would be a pivot position, and this would be a pivot position. But there's only one free variable, and that's not going to work because this eigenvalue is multiplicity 2. We need 2 free variables. So because we don't have enough, we can just stop right here and conclude that the matrix is not diagonalizable. So however many times it repeats, that's how many free variables you need. We didn't get them in this case. If you look at this, the upper left 2 by 2 block 7027. Anytime a matrix like this, where the 2 diagonal entries are the same, and we have an entry like this, like down here or up here, that's non-zero, that's a matrix that is not diagonalizable. Actually, I'm going to make a note of that up top. Okay, so here we have a repeated eigenvalue because the same value along a diagonal. Matrix of this form, if this entry up here is non-zero, is not diagonalizable, because when you take this matrix minus lambda times identity, we still have this entry here. You're only going to have one free variable when you really need two. And here I've written I've given a matrix as upper triangular. But if you transpose it, now it's lower triangular and the C is down here. Same thing. It's still not going to be diagonalizable. So this is one type of non-diagonalizable matrix that you can spot. So you can determine just by inspection that it's not. And if we take a look at the matrix we're just working with in this problem, here, this upper left 2 by 2 block is actually of that form where C is equal to 2 and lambda is equal to 7 in this case. So that's kind of a clue right there before you even start. That's going to turn out to not be diagonalizable. Last problem. So if a matrix is diagonalizable and can be factored in the PDP inverse, that factorization is not unique. So here, in this case, you are given A as well as P and D, and therefore P inverse. So if you're given an alternative D, so D, it's called D1. What will be the P1 that goes with it? Well, look how D1 differs from D. All that's done here is to swap the eigenvalues. So all you have to do to get to P1 that goes with this D1 is you also swap the column. Sorry, I have to be looking over here. P, swap the columns, and that's what's done here to get P1. Actually, swapping the rows of P inverse, that would complete the factorization. But as far as MyLabs is concerned, it's just asking for P1. So here, they swap the eigenvalues. So in P, swap the columns, and you're done. And it's just because each column of P is an eigenvector corresponding to the same diagonal entry of D. So here, the eigenvalue 5 has this eigenvector 1 and minus 1. Well, in D1, this element is 5, the second element. Therefore, the second column of P1 is the eigenvector 1 and minus 1. So, but yeah, to get your answer in MyLab, just swap the columns. And it's because they've swapped the diagonal entries of D, and that's it. So it's just making sure that eigenvalues and eigenvectors match up. So we've come to the end of this section and also this chapter. It introduces you to eigenvalues and eigenvectors and diagonalizing. So are there any last questions about this assignment? Okay, I will stop the recording here.